Okay, so luckily in this case, in the first problem, the bases are all identical in the numerator as well as the denominator. So the question now is the order of operations. Some people would like to cancel the numerator terms with the denominator term first, then proceed with whatever that's left in the numerator. Some would like to take care of the numerator terms, then simplify it with the denominator. At the end of the day, it is simply a matter of choice. So what I am going to do is take care of the numerator terms first. So since I have identical bases x, I can put that identical base and combine the powers, minus 9 plus 4, divided by x raised negative 5, which would give us x raised negative 5 over x raised negative 5, and they are the same, so they will get cancelled and we get 1. If we want to look at it from the quotient rule perspective, since the bases are identical, I can write it as minus 5, and when this denominator exponent goes to the numerator, it becomes positive 5. Minus 5 plus 5 is 0, and any number raised to the power of 0 is 1. So that is how we know that, the answer is 1. We've all been taught, okay, there is a numerator term and denominator term. They are the same. Let's just cancel it. And this is the reasoning behind it as to why it happens the way it does. Here we have another expression. So as I said, until you become experts with exponents, doing it in groups or in a term-by-term fashion would help minimize the amount of mistakes that you would make. So what I'm going to do, since every single term is in product in the numerator and denominator, I could split them and write it as individual terms. But if there are any plus signs or minus signs in the numerator or in the denominator, it's going to be a bit more tedious. So here, since there are no plus signs or minus signs among the terms, I'm going to split and write it as 18 over 3 multiplied by a over a raised negative 3 multiplied by b raised negative 6 over b raised 6. So as you can see, I've grouped all the numbers together, the a terms together, the b terms together, and I'll put a note here. This is only possible because the terms are in product. Otherwise, we can't do it. So going back, we can simplify each term. 18 divided by 3 is 6. The bases are identical in the second term, which is a, which means I could write it as a raised 1, which is the numerator power, minus the denominator power, so minus 3, that is the quotient rule, and b is the common base, minus 6, and if the denominator power moves to the numerator, it becomes minus 6. So we have 6 multiplied by a raised 4 multiplied by b raised negative 12. And since we want the answers only in positive exponents, we write it as 6 a raised 4 b raised negative 12 over 1. And if that term comes to the denominator, just the b raised negative 12 part, we would have 6a raised 4 divided by b raised 12. So here we have 30, I pronounce it as z, so z squared times z raised 5 divided by 55, z raised negative 4, z, same thing. Since all the terms are in product, I can split the numbers first. And put all the other terms that have z in them in the second part. 30 and 55 both will get cancelled by 5. 6 times 5 is 30, so we have 6. And 11 times 5 is 55, so we have 11. The bases are identical over there, so I can combine the numerator terms, 2 plus 5, divided by z raised negative 4. The bases are identical, so I just have to subtract the powers. So we get z raised 7 minus 4. So the answer is 6 over 11 multiplied by z raised 11. It is the same as 6z raised 11 over 11. So exponents play a key role in terms of scientific notation. When we have a really large number or a really small number, we want to write it in a very precise manner without making it look quite inefficient. What do I mean by that? We take a class in chemistry, we look at the size of atoms, we look at the size of electrons, and some of the sizes could be extremely small. Same with bacteria and viruses. Some viruses are the size of, 1 nanometers. In the sense we have 0.000000001 centimeters. So that is a very small number, and that is for a very small particle such as a virus. Let's say we're talking about the distance between Earth and let's pick Pluto. Then I don't know the exact distance, but let's just say, for example, it is 70 billion 650 million and 90 kilometers. And I know for a fact that can't be true. And we don't want to write it that way because it's quite lengthy. So we want to write it in a precise way, and that is done using the scientific notation, and we make use of exponents to do that. So what do we do? If we want to express small numbers, shouldn't say really, I should say so small numbers are typically expressed in negative exponents. On the other hand, large numbers are expressed in positive exponents. What do I mean by negative exponents? Ten raised negative 1, 10 raised negative 2, 10 raised negative 3, dot, 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 and it keeps on going. So negative 1, negative 2, negative 3, negative 10, 10 raised negative 50, and so forth. And by positive exponents, 10, 10 squared, 10 cubed, 10 raised 4, and so forth. And the base in this case is 10. All numbers that we talk about in math are base 10. Which is why the exponents that I wrote, they all have 10 as the base. Another key thing to note here, typically we move the decimal Now, I have to stress on the word typically, which means that this is not the only way or the only scientific notation that one can write, but common practice is to write it in such a way that I have a digit on the right-hand side of the decimal point. Okay, so here we have a large number, which is 31,250,000. So I want a digit to the right of the decimal point. So if I put a decimal there, I don't have, I should say right of the decimal and left of the decimal. So we do have one on the right and one on the left. Perhaps I shouldn't explain it that way because it is clear to me, but it may not be clear to you. Find a better way to explain this. How about this? Just do one digit to the left. So if I put the decimal there, I have 1, 2, 3, 4, 5, 6, 7 digits on the left and 1 to the right. So if I move that decimal over here, then I have 2 on the right and 5 on the left. If I move it here, I have 3 on the left and 5 on the right. So for me to have only 1 on the left, so the decimal has to be there. So we have to move the decimal from out here and to that position. And that is our objective. You have to keep in mind every number has a decimal associated with it. What do I mean by that? We write numbers as 10, 20, and perhaps 8, but 10 inherently means 20.0 and 8 means 8.0. So there is a decimal value. So the decimal in this case is at the very end and we've got to move it. So the way we write it is to have it as 3.125, and we want to see the number of places that we had to move the decimal to get to 3.125. So 1, 2, 3, 4, 5, 6, 7. So we have 3.125 times 10 raised 7. And that would be the scientific notation. And by 1 decimal digit to the left of the decimal, I meant this 3 that we see right over here. Again, the word of caution, this is not the only way to represent this number. For instance, I can move it by one more decimal to the left and write it as 0.3125. Since I moved the decimal to the left one more time, the power would be 10 raised 8. Or if I stopped, or if I moved to the right by 1 decimal, wanted to write it that way, I have to decrease the power 7 by 6 because I'm moving to the right. So the next problem, 0.0125, is a good case where we have to move to the right. Our goal is to write it in terms of 1.25. So we have 0.0125, and I'd like to have the decimal right over there. So I moved it once to the right, twice to the right. So I will have 1.25 times 10 raised negative 2. So the note here is negative exponents. Moving decimal to the right. In this case. And in the previous problem, positive exponents, we move the decimal to the left. So here is an example, which is 0.000053, and I want it to write it as 5.3 multiplied by 10 raised something, and that is our objective. So what we want is to move the decimal to that place right there. So how many steps would it take? 1, 2, 3, 4, 5. So it would be 5.3 times 10 raised negative 5. Now we can go further and say, let me move the decimal one more time to the right. So I'd get 53 times 10 raised negative 6. But keep in mind, 53 is 53.0, as I mentioned earlier. So you may say, oh, let me move it one more time to the right. So I can write it as 530 times 10 raised negative 7. So in short, any number can be written as 530 or 530.00000 and so forth. And I can keep on moving the decimal to the right. But each time I move it to the right, I have to decrease the exponent by 1. So exponents are quite important when we deal with scientific notations.